the organizers for inviting me to this nice conference. Yeah, so today I'll give a kind of high-level survey of a kind of research direction I've been interested in for the past 3 or 4 years on understanding sort of space-resolved local transport in interacting metals. This is work I've done with many of my group members who are highlighted here, together with experimental groups here at UCSB, led by Anya Jayek and Andrea Young. Okay, the motivation for the work that I'm going to do is a bit aspirational, but okay, let me just state it. This is kind of where we would like to go. Ultimately, I think, as we heard in the previous talk and a lot throughout this conference, there are a lot of observations of T-linear resistivity in so-called strange metals, but it's not really clear what the mechanism for this is, whether it's universal. There are many theories. There are sort of way too many theories that all have T-linear resistivity. So you can have, of course, classical phonon scattering at high temperatures, but maybe it's possible somehow to get low temperature, phonon T-linear resistivity. Maybe there's some sort of non-Fermi liquid and some Planckian non-quasiparticle physics. Or maybe it's something else. Maybe we haven't understood the mechanism for T-linear resistivity. And of course, this could depend on one material to the next. There's no reason a priori it has to be universal. One thing that I think is sort of awkward with this story is that oftentimes we focus so much on this DC linear resistivity that, and to say that it's Planckian, somehow we're using most of the data that we get out of that number itself. But that number, the bulk resistivity, is just one piece of a whole function, right? The sort of current two-point function or the conductivity. And so sort of guiding principle for what I'll be describing today is that it would be nice if we knew, if not the whole function, at least maybe that function along one of these two axes of wave number or frequency. Could we, for example, tease apart all of these different phenomena that will all give exactly the same T-linear DC resistivity? Okay.
So you said one of two axes. We know it along one axis. Omega, that's the optical conductivity.
Yes. Yeah. So that's my next point. So there's a long history of doing this. It's not an original idea. Okay. So there's a long history of looking at optical conductivity, especially in strange metals. I think we saw the data from this paper of Dirk's earlier in the conference. And I'm sure that I'm not a historian. I'm sure I've missed other people's work. But respectfully, I will argue that if possible, we would rather have sigma of k rather than sigma of omega. And I'll show you this in a few different examples where it turns out that there's physics that is interesting. We'd like to know, we'd like to measure it, but it's missed if you just look at optical conductivity. Okay. So I think space resolution is sort of the goal that we should aspire to, more so than time resolution. Okay. How do you do space-resolved, transport measurements? It's not easy because the speed of light is very large compared to the Fermi velocity. So it's much easier to look at finite omega rather than finite k. But there are mechanisms to study finite k. It's often indirect. The one that my collaborators here use is nitrogen vacancy center magnetometry. In a nutshell, you just scan this probe over a two-dimensional sample or a thin film of something three-dimensional. As you sort of push currents through this sample, the NV center will detect the magnetic fields generated by those currents, and you can basically use the Biot-Savart law to make a map of how the current is flowing locally in the sample, sort of non-invasively, or in vivo, as the biologists would say. Okay. And there are also other kinds of local probes. You can use scanning electron tunneling. There are local thermometers. So, this is not the only technique, but it's the one I'll sort of focus on today. Okay. So let me now sort of begin by describing what I think is the best understood example of a theory for space-resolved transport. which is the theory of hydrodynamic Fermi-liquids in metals. Maybe for once I'll spend more time talking about the kind of quasi-particle side of this conference. Okay, so let me imagine I have a metal. For the moment, let's just say it's a nice Fermi-liquid with well-defined quasi-particles. This sample may have some size, let's say W. Then, I have maybe electron quasi-particles here depicted in blue. And at finite temperature, these quasi-particles will have some scattering length, LEE, a sort of mean free path for collisions. And suppose that these collisions are mostly momentum conserving. For example, I have a small Fermi surface. Okay. I have lots of other crap in metals, so maybe these red blobs denote impurities. Okay. And the electrons, may scatter off of the impurities at some rate. I'll call that one LMR for momentum relaxing. Okay. And just with these ingredients, I'm not talking about Umklapp or phonons, etc. I can already identify 3 transport regimes. It's maybe 4 if you paid attention to Levitov's talk, but that's too complicated, so I'll stick to 3. Okay. If we look at sort of transport physics on scales that are very small compared to W, which in turn is the smallest length scale in the problem, if that's the case, then we will probe essentially single particle ballistic transport. Okay. If, on the other hand, the momentum conserving mean free path is very small compared to the width of the sample, but the sample is itself, or the scale on which we're looking, is itself small compared to this geometric mean of mean free paths, then we can see a regime of viscous transport. I'll sort of quickly derive that for you on the next slide. And then, if our length scales are too big, then we just see sort of ordinary ohmic transport, and that's ideally what we'd like to avoid. Okay, so, okay. If we focus for a moment on the sort of viscous, hydrodynamic, and ohmic or diffusive limits, then we can give a very nice and simple derivation for what we expect the frequency and wave number dependent conductivity to be. This will just come from solving the linearized Navier-Stokes equations. I'm not going to explain what all of these symbols mean, but these are hydrodynamic equations that couple together the density of charge and a velocity field, which is basically the momentum density. Okay. There are 2 important coefficients in these equations. The shear viscosity, eta, is proportional to the momentum conserving mean free path. And this parameter, which I've called alpha, this corresponds to a kind of friction on the fluid coming from momentum relaxation. And this parameter alpha is proportional to 1 over the momentum relaxing mean free path. Okay. So you take these equations, you say, well, I'm applying an electric field, which is e to the I kx minus I omega t. You solve these equations, it's a few lines of algebra, and you find that your, so note that the k should be transverse to the direction of the electric field. You solve these equations, and you find that sigma of k and omega is rho squared, that's my density squared, divided by an interesting denominator. If I take k and omega and set them both to 0, then I just get rho squared over alpha, and we see that all we're probing is the sort of momentum relaxing physics. Okay. If I set k equals 0, but I had finite omega, I see this Drude peak. And lastly, if I have k equals, or k not equal to 0, I can see this viscous contribution, which tells me information about this momentum conserving mean free path. So the point that I want to emphasize here is that only this red piece, only the viscous piece, sees the physics of these momentum conserving interactions. And these are probably more interesting to us in many cases than the momentum relaxing ones. We might hope that they're more universal and they don't depend on the sample quality and so on. Okay? But they're invisible if all you look at is sigma of omega. And the conclusions that I've said here are not sensitive to Galilean invariance or the existence of quasiparticles. So these are very general sort of comments about sigma. Okay. So now let me show you, there are many experiments now that have looked at kind of space-resolved transport in one form or another. I'll show you one that I like with my collaborators here. So here we're going to be looking at hydrodynamics in graphene. At finite density, graphene has an approximately circular Fermi surface. It's a very nice Fermi-liquid. Okay. And we're going to probe the sort of finite wave number conductivity in kind of two complementary ways. The first is that we're going to push current through a sort of spatial constriction. This is a nice geometry proposed in this paper from 2017. So the constriction, it's maybe a bit hard to see, but it's this little black inset here. If you have sort of ohmic transport, this is just like a conventional dirty metal LMR is small, you will see that the way current flows through this constriction is you get two kind of peaks at the edges of the constriction. So most of the current kind of hugs the wall. This is the lightning rod effect from E&M. Okay. If you have ballistic transport, you see that the way current flows through this constriction is approximately homogeneous. And if you have viscous transport, you see this kind of semicircle shape. Okay. These latter two are a bit hard to distinguish, unfortunately, but that's life. Okay. Anyway, you can in principle try to access this physics by just measuring the overall conductance of this device. But I think it's nicer to just directly image the current flows directly. What, sorry, is there a question? Oh, so this is the current density. So where you have bright colors, that means more current is flowing. And then here, this is just a line cut across the constriction. So again, this sort of peaks at the edges. This is using these NV center magnetometers. Okay, so if you do this experiment at the charge neutrality point in graphene, you see basically these ohmic sort of two peak structures. It's a bit more pronounced at high temperature than low temperature. I'll come back to that later. At finite density, we see ohmic transport at room temperature, which is expected as there's a lot of phonon scattering in these systems at room temperature. However, if you go down to lower temperature, this is 128 Kelvin, we see that this sort of two-peak structure disappears and you can see a single peak. And now you have to sort of ask which one is it? Is it 2 or 3? And they're very hard to tell apart, but we believe that it's sort of weakly viscous and, albeit with very large error bars, the sort of optimal fit to this data has a sort of LEE and LMR that's consistent with both measurements on our device and other experiments. Okay, so this is sort of an experimental illustration of how these space-resolved transport methods can be employed. Okay, we understand a lot about isotropic Fermi-liquid hydrodynamics. I don't know how much more there is to say, but perhaps surprisingly, a lot less is known about anisotropic hydrodynamics. And this is something that, at least in principle, should be very easy to find in experiment. I said in principle, this is hard in practice. But, you know, most metals are very anisotropic, but we still have materials that have small anisotropic Fermi surfaces. And so we might ask, you know, if we wanted to do transport experiments, you know, these space-resolved transport experiments on anisotropic systems, can we discover sort of new things that are impossible in graphene? And the answer is yes. So if we sort of allow for more generic, explicitly broken rotational invariance, there's a whole zoo of new transport coefficients that you can identify within hydrodynamics, even just keeping track of density and momentum. And with Galilean symmetry, which is a sort of emergent symmetry for an isotropic Fermi surface, basically all of them are set to 0. But as we go through the song and dance, the more symmetries we break, the more of these coefficients can be finite. So for example, if we break Galilean boost symmetry, this would be like going to low density in graphene. You can get, in principle, a bulk viscosity and what's called incoherent diffusion. If you have hexagonal symmetry, you can pick up what's called the rotational viscosity. This was something my student did in 2019. With square symmetry, you get a sort of another cubic viscosity. This is just like elasticity, so it's not very interesting. And most recently, we pointed out that with triangular point groups and below, you can actually get these kind of dissipative piezoelectric-like coefficients. So these are like hybrids between incoherent diffusion and viscosity. Okay. And we have a sort of full classification in this paper using sort of effective field theory methods. Okay. How do you detect any of these new coefficients? It actually can be very non-trivial, but maybe just to briefly highlight this paper, here we pointed out that if you design sort of clever geometries with multiple current leads, you can actually design experiments that sort of isolate, in particular, the existence of a rotational viscosity, which has never been detected in an electron liquid, but I believe should exist. So the experiment basically goes like this. If you choose voltages at the boundary such that current flows in and out through leads in the right symmetric patterns, then using local thermometry, if you detect heating at the center of this square, then you know by symmetry that you must have sort of dissipative physics in certain channels. So in the hydrodynamic limit, you can use this technique to basically detect the existence of rotational viscosities as well as these anisotropic cubic viscosities.
Can you give what rotational velocity is?
Rotational viscosity, in a nutshell, says that you have antisymmetric stress when you have vorticity in the fluid.
So it gives novel vortices, or what does it do?
So what it does is basically it's like the opposite of bulk viscosity. So bulk viscosity is like it's extra. There's extra dissipation when you squeeze on the fluid, and here you have extra dissipation when the fluid spins. So it's a very kind of lame effect from the point of view of dynamics, but it's a novel effect from the perspective of transport phenomena. This is forbidden in isotropic fluids by symmetries, but it's allowed in these anisotropic liquids. And at least as far as I know, this has never been discovered in experiment. So it's a prediction about the structure of hydrodynamics that I think can be seen. Okay. If you have, let's say, viscous versus ballistic transport, we saw that these are very hard to distinguish for isotropic liquids. But one other advantage of anisotropic systems is if you sort of squint carefully, you can see that the viscous and ballistic patterns become quite different in anisotropic liquids. So the ballistic pattern has this kind of shearing, and if you sort of looked at the antisymmetric part of this image in the x direction, you would be able to crisply distinguish these two transport regimes. This is using a sort of microscopic model of ABA tri-layer graphene, but this effect would be generic. Okay. Just to sort of quickly flash through two other examples. So space-resolved transport is also interesting sort of outside of the conventional electron hydrodynamic regime. Another setting where we believe this method will be quite striking is in thin films of superconducting materials. So superconductivity is characterized by sigma, right, diverging at k equals 0. But at finite k, sigma will not diverge. This physics is basically old. It's like 60s and 70s. As long as you have samples that are smaller than a millimeter, you can use the theory that I've described. And this should give you a kind of analog viscous flow with a very tunable momentum relaxing length. Okay? So we believe that superconducting thin films should also give rise to very striking non-local transport. We've also used we've also developed a theory for non-local transport in systems without quasiparticles. So you could imagine in particular that if you have a sort of non-Fermi liquid soup with no quasiparticles, you may have hydrodynamics on length scales that are sort of long compared to a Planckian length scale, which is h bar over k, or Bf times T. But what happens if we look at sort of space-resolved physics on scales that are short compared to the Planckian length scale? So there's no ballistic limit here. There's no quasiparticles. But we can use holographic methods, or ADS-CFT, to calculate the conductivity sigma of K, and we have an algorithm to generate the current flow patterns that should exist in this setting, and we find that there's a sort of nice ohmic to quantum critical crossover where you go from, again, this sort of two-peak structure to a single-peaked structure. And if we go back to that data from charge-neutral graphene, it's actually fit quite nicely by this model with a single fit parameter, which is sort of the effective conversion ratio between temperature and the Planckian length. The conversion factor that we find is actually quite similar to an optical experiment done in 2019. Okay. All right, so since I'm out of time, let me just quickly summarize. So new experiments, that have come online in the past 5-6 years can reveal space-resolved phenomena. I think this is quite exciting. Some of our predictions include this analog viscous flow in superconducting thin films, as well as the prospect of sort of crisp signatures of quantum critical transport on short distances. This requires quite high resolution, but this is something we believe we can access in sort of near-term experiments. I think most importantly, sigma of K has not been computed in so many microscopic models, and I think this is something that would be nice to remedy. So I hope that if not by my students, that other people start calculating this quantity. There are a lot of experiments that can then be done. All right, thanks.
Very nice. Just a comment, there is a classic experiment that would also measure the transverse conductivity at finite momentum, which is the skin effect. So the surface impedance tells you exactly the transverse conductivity on the scale of the skin length scale. So it's a wonderful way to see viscous behavior and so forth in these systems as well.
Okay.
Yeah, I was wondering, there is by the way, I really enjoyed your talk. There is a geometry that has been described experimentally and theoretically in a not so well-known paper in Physica, Helvetica Physica Acta in the 70s by a certain Stuckey. I think it's a paper that got cited 7 times or something like that. Two times of which was by me. And he used a Corbino geometry. So you let the current flow outward from the inner ring to the outward ring, and that also probes viscous effects because you dilute the fluid. And I wonder if you do you know that paper? And
I don't know that paper. I know other authors have recently started thinking about Corbino geometries. Yeah. I would argue that I still think this approach is a little bit cleaner because even in the Corbino geometry, you would still have to disentangle the sort of ohmic piece from the
Okay, but you could actually combine it. But you could do this, and maybe sure, maybe
if you can, etch the Corbino disk into your 2D sample, which in principle could be done, you could do that experiment. I think there are actually better geometries than either the Corbino or the constriction. This is sort of some ongoing work that my student is doing with the experimentalists here. But we think there are even better geometries that even for isotropic systems might cleanly distinguish different transport regimes.
Of course, I also hope that by mentioning this, the citation index of that paper will go from 7 to 8.
I see. Okay.
So early on, I think you put down this solution to your linearized Navier-Stokes equation, and then you had this expression, which was like Drude, except for the eta k squared on the bottom.
Yes.
So what's a reasonable estimate for eta? So usually we don't have a good way of measuring finite k effects or q effects in optical conductivity, but we usually despair to do it because we're comparing to the lattice scale. So my question ultimately is how big, what q or k could we measure? How big do we got to be on q or k to get some deviation of this?
I feel like I'm not going to tell you the answer in the units that you might like, but I can tell you the numbers that, you know, on the top of my head in the units I like.
Yeah.
So, eta, if you divide by this parameter m, you get a diffusion constant, which is Vs squared times LEE. So Vf, you know, for graphene is 10 to the 6, and LEE is going to be about 500 nanometers at 128 Kelvin. If you convert that to a frequency scale as appropriate, so diffusion constant times k squared for relevant devices, this is sort of in the gigahertz. So it's a very slow effect compared to.
So I need to be in the, you're saying I need to be in, have an equivalence in the gigahertz scale in order to.
Yeah, if you're looking at like gigahertz frequencies, you would pick up kind of diffusive quasi-normal modes.
And I can turn that to a momentum scale via Fermi velocity? No.
Yeah. So, well, okay. So if you measure like, let's say a resonance at omega equals minus I, that's another annoying thing, times, you know, diffusion constant k squared. From that diffusion constant, you can back out basically LEE by dividing by Fermi velocity squared. That's a sort of rough.
Yeah, you're right.
Schematic.
Not the units that I wanted, but maybe we can talk. Yeah.
Okay. Yeah.
So Andy, very nice talk. Can you say a few words about what boundary conditions are you applying at the transverse walls of the constriction when you solve these equations?
Yes. Okay. So this is we've basically kind of generalized the technique that comes from this paper. Effectively, so let me sort of say intuitively that what we do is we basically say we have no idea what the boundary conditions are, so we're just going to pick boundary conditions that happen to be easy to, you know, solve. So we can make these pretty two-dimensional pictures easily. What those boundary conditions are is they basically, what we say is that we apply electric fields sort of everywhere outside of the computational domain. This is where we etch onto the material. We apply external electric fields such that if you use J as like the integral of sigma of x minus x prime E of x prime, that there's no current that flows inside the constriction. This is probably something like a no-slip boundary condition, but I don't think they're exactly equivalent. And I have some ideas, but we've never really done very seriously how to try and generate like other families of boundary conditions. I think it's a difficult problem though. Yeah.
Yeah, great talk. I'm a little confused about what you said about non-local conductivity in a superconductor. Do you mean peppered supercurrent vector potential response, or do you mean response of a superconductor to an external electric field that creates particle-Hall imbalance?
This is just
very different
one,
scales.
it's the ordinary electrical conductivity. So the physics that goes into this is basically, so what's the sort of slow degree of freedom that's responsible for this diverging conductivity? And it's effectively related to the supercurrent, which is itself very closely related to vortex density. And so this A plus BK squared is basically the lifetime of vortex density fluctuations at wave number K.
Wouldn't you say the A is the superfluid stiffness?
So this A is basically flux flow resistivity.
Okay.
So if it's supercurrent, then shouldn't B be pure imaginary in this case?
This parameter B is the vortex diffusion constant, so I don't think it's imaginary. There are papers from the 80s by like Halperin and Zeppelius and others.
And you expect the length scale to be similar to supercurrent, or similar to the electric field penetration length in a superconductor?
So, okay, here I should also emphasize that we are, okay, maybe the title is misleading here. I intend to be just above TC. So as you sort of cool down, then you see that this flux flow resistance gets very small. But if you look at a length scale k, which would be something like the square root, or k, I guess, would be square root of a over b, then you would see that there's a sort of finite size effect kicking in. There are experiments that...
Maybe can you comment on the title, viscous superconducting film? What makes it viscous?
It's analog viscous, and it's just that this is a plus bk squared. That's the analogy.
So there is no real dissipation?
No, there is dissipation. I mean, diffusion is a dissipative effect, but it's not viscosity. There's no... That part is maybe misleading. But the analogy is to the form of sigma of k. We can talk more maybe offline.
What's being dissipated? Momentum or?
Supercurrent.
Okay, so this is P-paired response. Then B is imaginary. Yeah.
No.
Come back to the earlier conversation regarding the gigahertz activities. Can you actually get some information without directly measuring the current flow, but measure the map of the conductivity at different orientation at that kind of frequency, get some sort of complementary information from that momentum? What happens if you have a map of a conductivity, also electrical field you could map out? What will happen?
Sorry, so is the idea here that I use the same geometry, like the etched geometry, but look as a function of frequency?
Yeah, you can use the same geometry. You can put a field on and you can measure the field, or you can just make a local conductivity map.
Omega equal to zero conductivity, you mean?
So,
K equal to zero.
Complementary information on those?
Yeah, I think certainly in principle that could help. I don't know if that calculation has ever been done, but if I go back, yeah. But yeah, as I said, I don't know if anyone has ever calculated like finite frequency effects in this geometry, but perhaps even global transport measurements would be interesting at finite frequency.
Yeah, that's what I'm saying, that this kind of experiment also be developed.
I see. Yeah, I think it could be instructive, yeah.
Okay, maybe we can just thank again, Andy, and move on.